Screen is visible, students?
Yes, sir, visible.
Okay. In the last class, I discussed about how to solve the Laplace's equation to find the equation or the value of the capacitance. That was a discussion, and we solved 3 to 4 examples on the Laplace's equation. Next, we'll be starting with the magnetic field part, that is a steady magnetic field. Okay, next part of the module 3, the next half of the module 3, that is steady magnetic field. Now we know that electrostatics, whatever we have studied from module 1 till second half of module 3, it is about the static charges. It is about the charges which are at rest, which are constant, which are not moving. So such a study of the electric field related to the static charges is called as a electrostatics. It is electrostatics. Now here in the next part, what we are studying is about the magnetic field, right? Magnetic field. Now here, when we come to the magnetic field, we have a natural magnet, and because of this natural magnet is producing the permanent magnetic field. Because of the natural magnet is producing permanent magnetic field. Okay, and we also know the concept that any current carrying conductor produces the magnetic field surrounding it. If there is a current carrying conductor, then surrounding that current carrying conductor, there is a magnetic field. Yes. Now this magnetic field is constant or it is steady when the current is steady. When the current is constant, it is not varying with respect to time. When it is time invariant, that time the magnetic field is also time invariant, or we say that the magnetic field is constant or steady. Right? So such a magnetic field we call it as electromagnetics, or such a study we call it as electromagnetics. That is, electrostatics is a study of charges and its electric field at rest, whereas the electromagnetics is a study of the magnetic field which is constant or which is steady. So we have first part, we have studied electrostatics. The same concepts, almost similar concepts, we are going to study in electromagnetics also. Right? We'll see as we go on studying one after the another. Whatever concepts we have studied in electrostatics, the similar concepts will be studying in the electromagnetics. Okay, so this is how it all began, and we know that always the magnetic field does not exist individually. That means if there is a magnetic pole, then it is combination of north pole and the south pole. Individual magnetic poles cannot exist. There cannot be only north pole existing, or there cannot be only south pole existing. If the magnetic field exists, if the magnetic pole exists, then it is always the combination of the north pole and the south pole. That is what is producing the magnetic field. And when there are two poles, north pole and south pole, there is a magnetic field moving from the north pole to the south pole, right? North to the south, and then it completes the loop from south to the north. That means there are flux lines which are moving from north pole towards the south pole, and from the south pole towards the north pole, there are flux lines which complete the path, right? So like this, it forms a closed path here for the magnetic fields, right? So this is just a brief introduction, and whenever we consider the current carrying conductor, suppose if the direction of the conductor carrying the current direction is indicated by the thumb. So this thumb indicates the direction of the current. Okay, the current which is flowing in the conductor, its direction is given by the direction of the thumb, and the curl of your fingers, okay, the curl of your fingers, right? This gives the direction of the magnetic flux lines. According to the thumb rule, it says that if the thumb indicates the direction of the current flowing in the conductor, then the curl of your fingers, that indicates the direction of the flux lines, right? So this is how the direction of the flux lines can be found out using the thumb rule. There is one more rule called as the screw rule. Okay, according to the screw rule, if the direction of the current is towards the point towards the sharp point of the screw, right? And the rotation of the screw gives the direction of the flux. If there is a screw, right, and if the point of the screw, that is the sharp edge, the sharp point of the screw, if it gives the direction of the current, if it is towards the direction of the current, into the direction of the current, then the rotation of the screw will give the direction of the flux. So these are two points that we'll have to remember here. One is the thumb rule, which gives the direction of the flux lines or the magnetic field, and also the screw rule, which also gives the direction of the flux lines. With this introduction, let us move on to the study of magnetic field here. First that we'll be studying, it is the magnetic field intensity. The magnetic field intensity, as the name itself indicates, that it is the strength of the magnetic field. The strength of the magnetic field, strength or the weakness of the magnetic field is called as the magnetic field intensity. That is the quantity, how much strong it is or how much weak the magnetic field is, the magnetic strength is, that is nothing but the magnetic field intensity. The quantitative measure of strongness or weakness of the magnetic field is given by magnetic field intensity or the magnetic field strength. The magnetic field intensity at any point, suppose if we want to measure the magnetic field intensity, then the magnetic field intensity at any point in the magnetic field is defined as the force experienced by a north pole, unit north pole of magnitude 1 Weber, when placed at that particular point. How do you measure magnetic field intensity, or how do you define magnetic field intensity? Magnetic field intensity is defined as the force experienced by a unit north pole, of magnitude 1 Weber placed at that point. Unit north pole of magnitude 1 Weber, when it is placed at the particular point, how much is the force experienced by that unit north pole? That gives nothing but the magnetic field intensity. Magnetic flux lines are measured in Webers. The flux lines are measured in Webers, whereas magnetic field intensity is measured in Newtons per Weber. Magnetic field intensity is measured in Newtons per Weber. Okay. What about electric field intensity? What is the unit of electric field intensity? You have studied this in from module 1 to 3rd module. Unit of electric field intensity is, can anybody recollect? Unit of electric field intensity? Anyone? Can you all recollect unit of electric field intensity? Yes. Who will tell me the answer? Unit of electric field intensity? It is volt per meter. Is it not? Volt per meter is the unit of electric field intensity. Similarly, the unit of magnetic field intensity is Newtons per Weber. Newtons per Weber. Okay. It is denoted as H bar, and it is a vector quantity. Why it is a vector quantity? Because it is the measurement of force, depending on the force experienced by a unit north pole. Force is a vector quantity because it is along a particular direction. If you are applying the force from left to right, the object will move from left to right. If you are applying the force from right to left, the object will move from right to left. It is a vector quantity, and hence magnetic field intensity is also a vector quantity. This is similar to the electric field intensity E bar in electrostatics. Magnetic field intensity is similar to electric field intensity E bar in electrostatics. Magnetic field intensity is in electromagnetics, whereas electric field intensity is in electrostatics. Fine. The next definition that we are going to study here is the definition of magnetic flux density. As we know, electric flux density, it is the amount of flux or the amount of charge per unit area, right? We consider charge and flux both are similar. Charge and flux both are similar. Hence, the amount of charge per unit area, amount of flux per unit area, that is called as the electric flux density. Whereas in magnetic flux density, it is the amount of flux, quantity of flux per unit area, where the flux is the amount of flux crossing the unit area, and this flux is perpendicular to the area. So such quantity of magnetic flux, we call it as flux density. The total magnetic lines of force that is magnetic flux crossing a unit area in a plane at right angles to the direction of flux is called magnetic flux density. Magnetic flux per unit area. In electric flux density, it is charge per unit area or flux per unit area. Here it is flux per unit area. Okay, it is denoted as B bar. Magnetic flux density is denoted as B bar, and it is a vector quantity. It is also a vector quantity, flux density, because there is a particular direction in which the flux exists, is it not? Hence it is also a vector quantity. It is measured in Webers per square meter. The magnetic flux density is measured in Weber per square meter, which is also called Tesla. Which is also called as Tesla. This is similar to the electric flux density d bar in electrostatics. So magnetic flux density in electromagnetics, electric flux density in electrostatics. The unit of magnetic flux density is Weber per square meter or Tesla. Now, what is the relation between B and H? There is a particular relation between D and E. There is a particular relation between D and E. The relation between D and E is, you are all very much familiar with the relation between D and E. It is D is equal to epsilon times E. D is equal to epsilon times E. Similarly, the relation between magnetic field intensity and magnetic flux density. B is magnetic flux density, H is magnetic field intensity. There is a clear difference between the two, right? Try to understand clearly the difference between flux density and field intensity. We know the definition by now, right? B is equal to mu into H, as D is equal to epsilon into E. Similarly, in electromagnetics, it is B is equal to mu into H. What is mu? Mu is equal to mu naught into mu R. If it is free space, then mu naught value will be 4 pi into 10 raised to minus 7. As we have epsilon naught value in electrostatics as 8.854 into 10 raised to minus 12 farad per meter. Similarly, here for mu naught for free space, that is permeability is given by 4 pi into 10 raised to minus 7. This permeability mu is measured in henries per meter. It is measured in henries per meter. Okay. Now, if we want to define the permeability, permeability is defined as the ability to produce the flux lines surrounding the conductor. How to define permeability? It is the ability of the current conductor to produce the flux lines surrounding the conductor. This is what is called as the permeability. Okay. Next is one of the important questions. Consider the conductor carrying a direct current I and a steady magnetic field produced around it. Whenever we consider the direct current is the one in which it produces constant magnetic field. The DC current is constant. Yes or no? Alternating current is varying, fluctuating. DC current is constant current. As the direct current is constant, the magnetic field produced by the direct current is also constant. Consider a conductor carrying direct current I and a steady magnetic field produced around it. The Biot-Savart law allows us to obtain the differential magnetic field density dH bar. Magnetic field density dH bar. That means Biot-Savart law how much is the magnetic field intensity at a point P due to dl. Current passing through this differential length dl is I. I is the current which is flowing through this differential length. Okay. Then the angle between this differential element and the line joining the point P to the differential element is theta. And theta is the angle between the differential element, right, angle between the differential element and the point P, and the line joining point P to the differential element. R bar is the distance vector from the differential element to the point P. We are interested in finding the magnetic field intensity dH bar at the point P. We are interested in finding the value of dH bar. What is dH bar? It is differential magnetic field intensity at the point P produced or due to this differential current element, right? Consider differential length dl, hence the differential current element is IDL. Differential current element is I into dl. Small portion of the current element is I into dl. I into dl. Okay. This is very small part of the current carrying conductor. This is very small portion. If we consider the entire length, of the conductor here, we are considering very small portion of the differential element. This point P is at a distance of R from the differential current element. The point P, it is a distance of R from the differential current element. Then theta, what is theta? It is the angle between the differential current element and the line joining point P to the differential current element. Theta is the angle between the differential current element and the line joining point P to the differential current element. Okay. Then let us define Biot-Savart's law. Biot-Savart's law states that the magnetic field intensity dH bar produced at point P due to the differential current element IDL is the magnetic field intensity dH bar produced at point P, dH bar produced at the point P due to the differential current element IDL bar. It is directly proportional to the product of the current and the differential and dl. That is, dH bar is directly proportional to the product of the current I and the differential length dl. It is directly proportional to the sine of angle between the element and the line joining point P to the element. That is, it is directly proportional to sine theta, sine of the angle between the differential element and the line joining differential element to the point P. And it is inversely proportional to the square of the distance r between point P and the element. It is inversely proportional to square of the distance r between the differential element and the point P. This is the definition of Biot-Savart's law. Definition of Biot-Savart's law. Mathematically, the Biot-Savart law is stated as dH bar. According to whatever is the statement here, we have to just express it in the mathematical form. dH bar is directly proportional to product of the current and differential length dl, that is IDL. Then it is directly proportional to sine of the angle between the element and the line joining point P to the element, that is sine theta. It is inversely proportional to the square of distance r between point P and the element, that is divided by r square. R square comes in the denominator. It is inversely proportional. That is, mathematically, the Biot law is stated as dH bar is proportional to IDL sine theta divided by r square. Then if we equate this, we'll get the constant of proportionality. That is, dH bar is equal to k IDL sine theta by r square. dH is equal to k into I into dl sine theta by r square. What is k here? K is the constant of proportionality. The value of k is given by 1 upon 4 pi. Value of k is 1 upon 4 pi. Then dH bar, if we substitute k as 1 upon 4 pi, then we get dH bar is equal to I dl sine theta. K value is 1 upon 4 pi. So I dl sine theta by 4 pi r square. Correct. dH bar is I dl sine theta divided by 4 pi r square. Take it as equation 3. Take it as equation number 3. Let us express this equation in vector form. If we consider the vector form, then dl is magnitude of dl bar, magnitude of vector length dl bar. AR bar is unit vector in the direction from differential current element to point P. AR bar is the unit vector from the differential element towards the point P. That is unit vector AR bar. Yes. Then the form rule from rule of cross product. We know the cross product rule. If magnitude of dl into magnitude of AR multiplied by the sine of angle theta between dl and and AR bar. Am I right? DL cross AR bar, it is the magnitude of DL, absolute value of DL into absolute value of AR. Angle between the DL and AR bar is equal to 1. It is a unit vector. Magnitude of unit vector is 1, unity. And hence DL cross AR bar is equal to DL sin theta. Let us substitute this DL sin theta as DL cross AR bar. The main equation DL sin theta substitute as DL cross AR bar. DL cross AR bar. Then replacing in equation 3, DH bar is given by, instead of ideal sin ideal sin theta, I am replacing it by that is DL sin theta. I am replacing it by DL cross AR bar. DL sin theta in equation 3 is being replaced by DL cross AR bar. So it will be Ki DL cross AR bar divided by R square. That is the next equation. DH bar is IDL cross AR bar divided by 4 pi R square, ampere per meters. How to get the unit vector, students? What is the equation to get the unit vector? How do you find the unit vector? What is the formula? Anyone? Module 1, what all we have studied? Vectors. How do you find the magnitude of unit vector? Anybody? How do you find the magnitude of unit vector? Yes.
Given vector divided by square root of that coefficients of uh, ve- unit vectors.
Yes, correct. So we are dividing the given vector divided by square root sum of the coefficients of the given vector. Yes, that gives nothing but the unit vector. So AR bar is given by the distance vector R bar divided by its magnitude. This is the distance vector R bar from the differential element to the point P. So this distance vector divided by its magnitude, that gives the value of unit vector. Hence DH bar is given by, now substitute instead of AR bar in equation 4 as R bar divided by R bar, magnitude of R bar divided by R bar, vector divided by the magnitude. So it is DH bar is equal to ideal cross AR bar is R bar divided by R bar vector, it is divided by magnitude R. So R bar divided by 4 pi R cube, R square into this R, that will be R cube, ampere per meter. These equations 4 and 5 are the mathematical form of Biot-Savart's law. Equations 4 and 5 are the mathematical form of Biot-Savart's law. Okay. Here we have found out for differential length, that is small element. Here we have considered small portion of the complete length of the conductor. If we want to find for the complete length, then what we are supposed to do? We have to integrate. Correct? We have to integrate this small portions to get the magnetic field intensity due to this entire length of the conductor. That is the next equation. Entire conductor is made up of all such differential elements. Hence, to obtain total magnetic field intensity H bar, the above equation 4 will take the integral form. Equation 4 will take the integral form as integral dH bar, that gives the total magnetic field intensity H bar, that is integral of IDL bar cross AR bar divided by 4 pi R square. So it is a closed integral IDL bar cross AR bar divided by 4 pi R square. We have to take the closed integral because it is a closed path. We know that magnetic field or the current always flows in a closed path. Can the current flow in a open loop? No. Current can never flow in a open loop. Current always flows in a closed loop, and hence the magnetic field is also complete. It is also closed. Okay, it is also closed. Okay, there is a loop formed for the magnetic field, and hence we are taking the closed integral. H bar is equal to closed integral IDL bar cross AR bar divided by 4 pi R square. Take it as equation number 6. Now here we have considered the differential element as point 1 and the point P as the node number 2 or the point number 2. If the current element is considered point 1 and the point P intensity is given by I1 DL1 bar cross AR12 bar divided by 4 by r12 square. Just I'm replacing the AR vector in equation 6 by AR12. Source is 0.1, destination is 0.2. So it is from AR12 bar, AR12 bar. Then this distance vector will also be from source to destination. It is by taking it as R12. While calculating, we take the difference from destination to source. But when representing the vector, we take it as R12, capital R12 from source to destination. But when doing the calculation, it is opposite. We take destination first minus the source coordinates. Yes. Where I1 is current flowing through dl1 at point 1. dl1 is differential vector length at point 1. Current flowing through the differential element is I1. dl1 is the differential vector length of the differential element at point 1. AR12 bar, it is a unit vector in the direction from element at point 1 to the point at point 2, point B at point 2. Then AR12 bar, as we know that it is given by the distance vector divided by its magnitude. R12 bar divided by magnitude of R12. Therefore, H2 bar will be equal to closed integral I1 dl1 bar cross AR12 bar. It's a cross product. Note that it's a cross product. It doesn't mean that it is a multiplication. Right? It is a cross product. Please note that I1 dl1 bar cross AR12 bar divided by 4 pi R12 square ampere per meter. Take it as equation number 8. This is called as integral form of Biot-Savart law. Integral form of the Biot-Savart law. Okay. So here we have gone through the definition of Biot-Savart law. What is Biot-Savart law? Why it is used? Application of Biot-Savart law. Then next is, here we have considered a differential element, small portion of the conductor. Then we have defined what is Biot-Savart law, definition of Biot-Savart law statement. Accordingly, we have written the mathematical equation, and we have found out the equation for the magnetic field intensity in differential form. dH bar is equal to IDL bar cross R bar divided by 4 pi R cube, or dH bar is equal to IDL bar cross AR bar divided by 4 pi R square ampere per meter. And also in the integral form as H2 bar is equal to closed integral I1 dl1 bar cross AR12 bar divided by 4 pi R12 square ampere per meter. Right, students? Any difficulty appeal here, students? Any questions? Any difficulty appeal here? Yes, please. Any difficulties up till here in the derivation part or in the starting initial beginning? Any problem in understanding? Everyone understood the derivation? Was it clear? Derivation is important. You have to practice it. Okay. Any questions as such? Any questions here?
No, sir.
Right. Take this example, students. We'll solve the example on Biot-Savart's law. Find the incremental field strength at P2 due to the current element of 2 pi Az bar microampere meter at P1. The coordinates of P1 and P2 are 4, 0, 0 and 0, 3, 0 respectively. Note down the example. Find the incremental field strength at P2 due to the current element of 2 pi Az bar microampere meter at P1. The coordinates of P1 and P2 are 4, 0, 0 and 0, 3, 0, 0, 3. Note down the example. You all can note down the figure also, this figure also, right? This figure also you all can note down. So in the question, what they have given, incremental fields is dh bar, you have to find out at due to the current element and coordinates of 0,3, 0. Hold on quickly, students. Is it noted down, students?